Concrete beam failures engineering fault line. Concrete beam failures represent a significant concern in structural engineering due to their direct impact on safety and serviceability. Beams function as primary load resisting members, and their failure can result in partial or total structural collapse. A thorough understanding of failure mechanisms is therefore essential for ensuring structural reliability, minimizing risk, and improving engineering design practices. Concrete beams are structural elements designed to resist bending moments and shear forces through the composite action of concrete and steel reinforcement. Concrete primarily resists compressive stresses, while steel reinforcement carries tensile stresses. Structural failure occurs when this composite action is compromised due to deficiencies in design, materials, construction, or long-term deterioration. Concrete beam failures can be categorized based on the governing failure mechanism, including flexural failure, shear failure, bond failure, and compression failure. Each failure mode exhibits distinct structural behavior and damage characteristics. Accurate identification of failure type is critical for effective diagnosis and remediation. Flexural failure occurs when the bending demand exceeds the beam's moment capacity and is typically characterized by tensile cracking and gradual loss of stiffness. This failure mode is generally ductile and provides visible warning signs. In contrast, shear failure is brittle in nature, often occurring suddenly near supports where shear forces are concentrated, posing a serious safety risk. Crack patterns serve as important indicators of structural distress in concrete beams. Flexural cracks typically appear as vertical cracks near midspan, whereas shear cracks develop diagonally near supports. The orientation, distribution, and progression of cracks assist engineers in evaluating structural behavior and determining appropriate corrective measures. Concrete beam failures commonly result from multiple contributing factors rather than a single cause. These factors include inadequate structural design, poor material quality, construction deficiencies, environmental exposure, and unforeseen loading conditions. A systematic evaluation of these causes is necessary to prevent recurrence in future projects. Reinforcement corrosion is a major contributor to the degradation and failure of concrete beams. Corrosion products occupy a greater volume than the original steel, inducing internal stresses that cause cracking and spalling of the surrounding concrete. This process significantly reduces reinforcement capacity and weakens the bond between steel and concrete. Improper reinforcement placement adversely affects the structural performance of concrete beams. Errors such as insufficient concrete cover, incorrect bar spacing, or inadequate anchorage reduce load transfer efficiency and structural capacity. These issues often arise from poor construction practices or inadequate supervision on site. Crack propagation is a progressive deterioration mechanism driven by repeated loading, environmental exposure, and material aging. As cracks widen, they facilitate the ingress of moisture and aggressive agents, accelerating reinforcement corrosion and further compromising structural integrity over time. Sound design principles are fundamental to ensuring the safety and durability of concrete beams. These principles include accurate load assessment, appropriate material selection, compliance with design codes, and provision of adequate safety margins. Proper design aims to promote ductile behavior and prevent sudden failure. Reinforcement detailing plays a critical role in ensuring effective structural performance. Proper bar anchorage, development length, spacing, and concrete cover are necessary to maintain composite action and control cracking. Inadequate detailing frequently leads to premature distress and reduced service life. Shear design requires particular attention due to the brittle nature of shear failure. Adequate shear reinforcement must be provided to resist diagonal tensile stresses and enhance ductility. Conservative shear design, as prescribed by design codes, is essential to prevent sudden and catastrophic failure. Case studies of concrete beam failures provide valuable insights into common design and construction deficiencies. These real-world examples illustrate the consequences of inadequate analysis, poor detailing, and insufficient quality control, offering important lessons for engineering practice. Flexural failure analysis involves assessing bending moments, reinforcement ratios, crack development, and material behavior. Through post-failure investigation, engineers can identify whether failure resulted from design inadequacy, overloading, or long-term degradation effects. Examples of well-designed concrete beams demonstrate the effectiveness of proper design, detailing, and construction practices. Such beams exhibit controlled cracking, acceptable deflections, and satisfactory performance throughout their intended service life. Quality control is a critical component of structural safety and must be maintained throughout design, construction, and service stages. Regular inspections, material testing, and adherence to established standards are essential to ensure long-term structural performance. In summary, concrete beam failures are largely preventable through rigorous engineering practice. Emphasis on proper design methodology, accurate detailing, quality construction, and proactive maintenance significantly reduces the risk of failure and enhances structural reliability. Ultimately, engineers and construction professionals bear the responsibility of applying these principles to safeguard public safety. Continuous learning from past failures and adherence to professional standards are essential for advancing resilient and sustainable infrastructure.